Good morning to all. I am Shravani SS, Assistant Professor of EEE Department from Adiman College of Engineering, Hosur. I am handling Basic Electrical and Electronics Instrumentation Engineering paper. Today we are going to discuss about the basic laws. Those are Ohm's law and Kirchhoff's law. The first topic we are going to see Ohm's law. Ohm's law, the law which provides the relationship between voltage, current and resistors in an electrical circuit. It provides a relationship how it behaves when all together flows in a electrical circuit. So the statement of the Ohm's law are: at constant temperature the temperature should not change. At constant temperature the ratio between the potential difference is voltage across the two ends of the conductor and the current I through it is constant. It means the temperature does not changes. At that time the ratio between the voltage across the two ends of the conductor and the current that passes through the conductor is constant. That gives V by I equal to constant. And there is a resistance R between the 2 points of the conductor. R will replace as a constant. So V by I equal to R. This all happens at a constant temperature only. And we can frame other forms of Ohm's law by using the V by I equal to R. Those are I equal to V by R or V equal to I by R. These two forms of formulas we can frame by using the Ohm's law. This all will works at only in a constant temperature. And the next point is the limitations of Ohm's law. There are some limitations to follow the Ohm's law. Those are: first limitation, Ohm's law does not apply to all non-metallic conductors. It can apply to only metallic conductors. Non-metallic conductors means, for example, silicon carbide. It can apply only for metallic conductors, and it does not apply to non-linear devices such as Zener diode transistors, etc. It can apply only for linear devices. And one more limitation, Ohm's law is truly for metallic conductors, as we discussed earlier, only at a constant temperature. If temperature changes, the law is not applicable. These three limitations are more important while following the Ohm's law. Under these limitations only the Ohm's law will be applicable. Next, so finally the Ohm's law will be it's provide relationship between voltage, current and resistor at a constant temperature. Next topic is a Kirchhoff's law. Kirchhoff's law has two types: Kirchhoff's current law and Kirchhoff's voltage law. As the name itself, we can say that Kirchhoff's current law is going to discuss about how the current flows or behaves in a circuit. As the same way, Kirchhoff's voltage law is going to discuss about how the voltage flows or behaves in a circuit. So the first law, Kirchhoff's current law. First we are going to see the Kirchhoff's current law. Before going to the statement, we have to know the main points. Those points are: the first point, current cannot be stored in any point in a circuit. Current cannot be stored. Why? Current means the flow of electrons. The flow should happen. It cannot store. If once enter the current, it should leave the circuit. This is the first point. And the amount of current entering to a point must leave the point. So these 2 points should consider. Based on these 2 points, the statements are given. Statement 1. In an electrical circuit, the sum of the currents flowing towards a junction point is equal to the sum of the currents flowing away from the junction point. Second statement. In an electrical circuit, the algebraic sum of all the currents meeting at a junction is equal to 0. Both the statements are same in a different way. The output will be same. So to proving the Kirchhoff's current law, consider an electrical circuit in which 5 conductors are connected. Here I have connected 5 conductors to a node A. But for the 5 conductors, each conductor carrying a current. And the current is flowing, some currents are flowing towards the junction, that means towards the node, and some currents flowing away from the junction. So the currents which are flowing towards the junction we can call as incoming currents. The currents which are flowing away from the junction we can call as outgoing currents. Here I1 and I5 is flowing towards the junction, we can call as income currents. I3, I4, I2 is flowing away from the node, we can call as outgoing currents. So to prove the statement 1 from the circuit, what is the statement 1? Sum of the incoming currents is equal to sum of the outgoing currents. Here what are all the incoming currents? I1 and I5. Those should sum. I1 plus I5 equal to sum of the outgoing currents. What are all the outgoing currents? I2, I4, I5. So I1 plus I5 equal to I2 plus I4 plus I3. This derivation, this equation are derived from statement 1. To prove the statement 2, what is the statement 2? Sum of the all algebraic conditions, sum of the all currents that entering into the or having that connecting to the node is equal to 0. Okay. While doing sum, we need to assign positive and negative sign. For the incoming currents, those currents that entering into the node, we are assigning the positive, and the outgoing currents, those currents are away from the node, going away from the node, can be negative. Based on that, I2, I3, I4 are outgoing currents, so we are giving negative. I1 and I5 are the incoming currents, so we are giving positive. That all things is equal to 0. Now the positive are bring to one side and the negative are bring to another side. Finally, we will get I2 plus I3 plus I4 is equal to I1 plus I5, the equation 2. By observing the equation 1 and equation 2 that we get from the statement 1 and statement 2, both are same, remains same. Even though we assume incoming current, so here I assume incoming current as a positive, outgoing current as a negative. But if you assume incoming current as a negative, outgoing current as a positive, the same result we are going to get. So the assigning the signs is not it's just an assumption, so we can change. So finally, the Kirchhoff's current law means sum of the incoming currents that is equal to sum of the outgoing currents. The current should not store in any point in a circuit. Next one, Kirchhoff's voltage law. Kirchhoff's voltage law says that how the voltage behaves in a circuit. So here we have two statements. How the current law is sum of all the currents, like here also sum of all the voltage drops. Statement 1 says, in an electric circuit, the algebraic sum of all the potential rise and drops in a closed path is equal to 0. Statement 2 says, the sum of potential rises is equal to sum of potential drops in any closed path of an electrical circuit. Here it is in a closed path. In Kirchhoff's current law it is an open path. Kirchhoff's voltage law, it's compulsory a closed path. Both the statements are the same output. To prove that statements, first I am considering a electrical circuit with one source and 3 resistors, and the current are flowing through the resistors. The direction of the current as shown, and assigning A, B, C, D nodes. The voltage across the resistor is taken as a drop, and the supply voltage across the supply is taken as a rise. Both voltage drop and rise we have a positive and negative signs. Here the voltage drop we are taken as a voltage across the resistor, voltage rise we taken as a voltage across the battery. So both voltage drop and rise we have a positive and negative sign. Before proving those things, we have to assume some things. You can observe that in the previous circuit I didn't draw any assuming direction inside the circuit. Now you can see the one assuming direction that I drawn inside the circuit. To prove this equation, we have to draw the assuming direction inside the circuit. That should be either the assuming direction should be in a clockwise or in a anti-clockwise. Here I assumed the direction in a anti-clockwise direction. Now with the help of this assuming direction and the current that the direction of the current that passes in the branch, we are going to derive the equation. That how it means, under the circuit I have drawn some resistors and then battery. See here, the between A and B we can say as a branch. The path that allows the current to flow is a branch. The current that flowing in the path is a branch current. See, that branch current and the assuming direction, branch current direction and assuming direction is in the same direction, then I am going to assume that sign as a positive voltage drop. If the branch current direction and the assuming direction is in a opposite direction, then I am assuming that is a negative voltage trace. We can assume by reversing these signs. It is not a compulsory that this should be a positive, this should be negative, but we can change it, but it should be in a correct format. Then see, for the battery, if the assuming direction enters the negative terminal first, then it is a negative voltage rise. If the assuming direction enters the positive terminal of the battery first, then it is a positive voltage drop. With the help of this all the assumptions, I am going to derive the equation. Now let us see how it going to happen. See, first the node from A to B, there is a current R1 resistor is there. Here in the current through the R1 resistor, the direction of the current through the R1 resistor is same as the assuming direction. So it is a positive voltage drop. Thus, so I given positive IR1. From B to C, the current from B to C direction, the direction of the current from B to C is same as the assuming direction. So it is also positive, then positive IR2. The direction of the current between C D branch is same as the assuming direction. So both the directions, branch current direction and assuming current direction are same. So it given as a positive IR3. But here see, the assuming direction touches the negative terminal of the battery. If the assuming direction touches the negative terminal of the battery, I assumed here it as a negative voltage rise. So it is a minus E. According to the statement 1, the algebraic sum of all the potential rise and drops in a closed path is equal to 0. Right. So here the voltage drops are across the resistors. That is IR1, IR2, IR3. Voltage rise are across the battery. It is a E. The arithmetic sum is equal to 0. So I am adding all the things that equal to 0. It proves the statement 1. From the equation 1, the positives are in one side. I am arranging the positives are in one side and negative are at the other side. Then it gives sum of the voltage rise is equal to sum of the voltage drop. This proves the statement 2. See, the statement is sum of the potential rises is equal to the sum of the potential drop in any closed circuit. Here this equation 2 proves the sum of the voltage rise. It is a E, sum of equal to sum of the voltage drops. That is the across the resistors IR1, IR2, IR3. So both the equations are the same. Both the statements are the same. From the voltage law, we can say that sum of the potential drops in a circuit is equal to sum of the voltage potential rises in a circuit, that it is a closed path. These are all the 3 basic laws which proves how the current and voltage behaves in a circuit and what is the relationship between voltage, current and resistors can prove by Ohm's law. So today it is the end of the session and thank you all.